Okay, let's dive right into this explainer. We're going on a continuous, extreme journey today, starting from the sunny surface of the ocean and plunging all the way down to the deepest, most hostile point on planet Earth. We'll be looking at the absolute limits of our own bodies, some incredibly bizarre animal adaptations, and the sheer jaw-dropping engineering it takes for us to survive an environment that, honestly, actively wants to obliterate you.
To start things off, let's indulge in a bit of a dark thought experiment. Just imagine slipping beneath the waves. No submarine, no diving suit, you are completely unprotected. What exactly would the crushing weight of 11,000 meters of water do to your body as you sank into the Mariana's Trench?
Well, the reality is absolutely brutal. In mere seconds, way before you could even drown, your rib cage would literally implode. See, your body is about 60% water, and water is mostly incompressible. So the pressure wouldn't necessarily compress your tissues, but it would instantly crush every single air cavity you possess. Your lungs would be shrunk down to the size of apples. Your eardrums would shatter. You'd basically be squeezed into a biological marble as all your vital organs shut down, and the near-freezing temperatures down there would only speed that process up.
So the really crucial point here is that at the absolute bottom of the ocean, a place known as the Challenger Deep, the pressure hits an unfathomable 15,750 pounds per square inch. That's 1,086 bars of pressure, which is over 1,000 times the normal atmospheric pressure we're all comfortably sitting in right now.
To put that into perspective for you, it is literally like having a freight train balanced delicately on your skull. Or imagine 100 adult elephants standing directly on your head. It's a physical force so extreme it genuinely defies our everyday imagination. And that naturally raises a big question. How deep can a human actually go before our biology just flat out breaks?
Section 1. The Human Limit. Breaking Biology. For the longest time, doctors were absolutely convinced that if a human went past 30 meters, our total lung capacity would be reduced to its absolute minimum, resulting in total lung collapse. But human ambition is wild, isn't it? Every time science set a hard limit, freedivers just blew past it. Back in 1968, Jacques Mayol dove down to 70.4 meters. And then, I still can't really believe this, but in 2007, Herbert Nitsch set an astounding no-limits freediving record of 214 meters. He completely overrode the most basic, overwhelming human urge to breathe.
This whole thing brilliantly illustrates Boyle's law. It's a fundamental rule of physics that dictates as you descend, the water pressure doubles every 10 meters, and so the volume of air inside your lungs violently compresses. At Nitsch's record depth, his lungs were compressed to less than half a liter in size. This massive drop in oxygen saturation pulls a diver dangerously close to what's called a shallow water blackout. That's a hypoxic loss of consciousness that can so easily lead to drowning.
Now you might be thinking, well, why not just bring your own air, right? Well, if you breathe compressed air, like a scuba diver does, you just introduce entirely new ways for the ocean to kill you. You aren't just fighting the water anymore, you are fighting the physics of the gases absorbing directly into your own bloodstream. Breathing compressed air at depth means that as the pressure increases, gases like nitrogen dissolve heavily into your body's tissues. If you head back up to the surface too fast, that dissolved nitrogen comes rapidly out of solution and it forms deadly bubbles in your blood. That's a painful and highly lethal condition known as decompression sickness, or the bends. Or alternatively, at deep depths, that same high-pressure nitrogen can trigger this dangerous euphoric disorientation called nitrogen narcosis. It essentially depresses your central nervous system at the exact moment you need your wits the most.
Section 2. Nature's Deep Sea Divers. Evolving for the Abyss.
While our human air cavities become deadly crushing traps under immense pressure, marine mammals like the Weddell seal or deep-diving whales totally thrive in this environment. They don't just survive the crush, they completely embrace it.
The contrast here is just wild. When a human descends too deep, our rib cage fractures and our tissues rupture as those lungs painfully compress. But whales and seals, they intentionally collapse their lungs entirely. By pushing the air completely out of the gas exchange surfaces of their lungs, they just completely bypass the risk of barotrauma and prevent the nitrogen absorption that causes the bends in the first place. They survive this extreme squeeze through a beautifully orchestrated series of biological cheat codes. Step 1. They trigger the mammalian diving reflex, which dramatically slows their oxygen consumption. Step 2. They execute a thoracic blood shift. Basically, blood rushes to the chest cavity to physically fill the empty space left by their shrunken lungs. And step 3, they rely on flexible, cartilage-reinforced airways that can compress completely without suffering any tissue damage at all.
Section 3. Life in the Abyss. The Hadal Zone.
Sinking further, past
past 6,000 meters, we cross an imaginary line into total darkness, where human biology is completely irrelevant. Welcome to the Hadal Zone. Named after Hades, the Greek god of the underworld, you'd probably expect a bunch of terrifying sea monsters down here, right? But researchers who have actually been here describe it very differently. They call this near-freezing, pitch-black ecosystem incredibly peaceful, and note that it's surprisingly devoid of the deep-sea monsters of our nightmares.
To survive the unbelievable pressure down here, animals have completely discarded anything resembling an air cavity. There are zero gas bladders. Instead, these creatures use transparent gel rather than skin and scales. As deep-sea researchers put it, gel is simply the cheapest biological buoyancy available when you need to conserve every single ounce of energy.
Take the snailfish, for example. Filmed at an astonishing 8,336 meters, this is the deepest recorded fish ever found. And it turns out it survives using a translucent body, extremely low bone density, and a highly specialized chemical called TMAO. This chemical is an osmolyte, and it actively counteracts the crushing external force that would otherwise literally pop its spherical cells like microscopic water balloons.
And the challenges down here aren't just physical, they are chemical. Below 5,000 meters, the very chemistry of the seawater fundamentally changes due to pressure and what's known as the carbon compensation depth. If you were to touch a snail that lives below this depth, its calcium carbonate shell wouldn't be hard. It would actually feel as soft as wet paper.
Section 4. Engineering the Deep. Surviving the Mariana Trench.
We've finally reached the very bottom, descending into the Challenger Deep. This is a realm we can only visit by relying entirely on miraculous, cutting-edge engineering. To give you a sense of the sheer scale of this depth, if you dropped a simple pebble off the side of a boat, it would fall for over an entire hour before finally resting on the absolute bottom. Descending almost 11,000 meters is such a grueling journey that when filmmaker James Cameron built his deep-sea Challenger submersible, he designed it to plunge vertically. It was built to slip rapidly like a torpedo straight through the water column just to save time on the commute. To prevent the sub from shrinking or violently cracking under the 15,000 plus psi, traditional materials just weren't going to cut it. Engineers had to invent a brand new synthetic foam called ISOFloat to provide both buoyancy and structural integrity. And as for protecting the massive battery banks from being crushed, they brilliantly housed them in silicone oil connected to, of all things, ordinary medical drip bags. As the pressure rises, seawater inflates the bags, balancing the internal pressure without ever touching the sensitive electronics. Honestly, it's genius.
But going down is only half the battle. Coming back up is a literal matter of life and death. The sub descends using 1,000 pounds of steel weights, held on by electromagnets. If those weights don't detach at the bottom, the pilot is forever trapped. So they built in 4 redundant fail-safes. The weights drop automatically if power fails, they can be commanded acoustically from the surface, there's a heat-activated frangibolt to sever the connection, and incredibly, they even use a galvanic wire designed to chemically dissolve in seawater after 13 hours. You know, just in case everything else fails. Yet, for all this incredible effort to reach the most remote place on Earth, the most shocking discovery at the bottom of the world isn't a new alien fish. It's us. Scientists have found that human trash, microplastics, and highly toxic flame retardants banned way back in the 1970s have beaten us to the bottom. These toxins are currently resting inside the guts of the local Hadal fauna. In some trenches, researchers have even noted a tragic 10-to-1 ratio of plastic bags to deep-sea animals. We've spent billions of dollars and countless hours overcoming the strict rules of biology and physics just to briefly visit the abyss. But the true takeaway from this explainer is a lingering, pretty uncomfortable question. If we possess the brilliance to engineer our way into the most hostile, unreachable environment on Earth, why are we turning its most pristine depths into a cesspit? It's a profound reminder that no matter how deep we go, we are always leaving something behind in the dark.